Okay, so this is my solution to the measurement problem. I've decided that the relativistic slide rule could replace the wave function, in which case it can go into superposition, so you can just add them together. And that's what I've done here. I've simply taken my wave function and then I've put it in a superposition with another wave function, or with itself. Like that. Okay, so you've got photons in that ray coming in. So they're just photons, those dots. They come in and then they go through the slit there, get diffracted, head off here, and now here's the particle, and this is the a line of simultaneous space, which is like the surface of a material, whereas this line here, which is perpendicular, that's the normal, that's the line of simultaneous time. So at this point it can either refract or it can be transmitted to the screen. Let's say that this is the screen where the photon is going to be detected. Okay, so it doesn't, you don't need any collapse of the wave function anymore. And now I'm just going to go back to all the ideas that I've had leading up to this idea. So I've played around with wave equations. These are the wave equations. And I played around with just adding the wave equation for wavelength to the wave equation for the period. And as a result, I was getting what I thought might be photons, wave packets. In other words, I was using my L and my T to create wave packets. And then see at high volume it's a wave packet, and then at low volume it's just a regular wave. Okay, but that's not working out. Then I tried putting L to the power of T, because I thought, well, I've only got an L and a T to play with, and that gives a proper probability density function. So here you can see I've got them in superposition, these black things there, the probability density functions. But that's not really working out either, so forget about that. And for a long time I've been playing around with just circles where I thought the particle could be emitting quantized waves, say just waves, and then I was getting all sorts of pretty interference patterns. But of course this doesn't solve the problem, because this doesn't solve the measurement problem, because the particle could be collapse into any of those superpositions. A whole lot of them. So even if I was to figure that out, I still wouldn't have solved the measurement problem. So basically, waves are the problem. We don't detect the wave function, we only measure photons. Okay, so I'm ending up with waves, rays of photons. And now I don't need to collapse anything. All I've got to do is figure out how the photons get to the detector, where they're detected. And so I'm imagining that the relativistic slide rule basically replaces Schrodinger's wave function. So the relativistic slide rule is the wave function, and because it's a wave function, it can be in superposition with itself. So you just add other wave functions. Because I had a problem of figuring out whether the photon might go left or right once it gets through the slit. I couldn't decide. So let's just add in a whole lot more rays, because now that I'm in a superposition of relativistic slide rules, I've got a superposition of photons. So now I've got this So you might have photons coming in, going through the say that slit and that slit, and then because the relativistic slide rule is in a superposition with itself, you've got this situation where it's symmetrical. So you see you've got B there, and you've got a B there. Oops. Oh, that's a picture of one, so that's no good. So when it hits the slit, it's in a superposition. It goes left and right in a superposition. And so it goes through goes right there and goes left there. Then these reflected rays meet up, and then you get transmission and transmission. But overall, you get a peak in the middle here, and you get another peak up here, so these narrow gaps there, what you call constructive and destructive interference, whereas the big wide boxes are constructive interference. So that's where you find the photons. So that's the idea, roughly.